затушу, сейчас посмотрим.
Я сейчас проверю. Пока ничего не видно.
Ну, ничего не видно. Может быть, и не ту камеру. Ну, слот есть, да?
Тоже, на самом деле, кажется, его не очень видно.
Да, что-то, а можно кому-то написать?
Да, я сейчас напишу.
Ага, спасибо большое. Ну, как всегда, раздолбать это. Скорее всего. Да. Что просто, типа, праздники, что там, зачем праздноваться?
Что-нибудь такое.
А?
Что-нибудь такое.
Да.
Ну, в общем, я написал. Думаю, кто-нибудь сейчас ответит.
Они умеют создать слот онлайн, да?
Ну, должны уметь. Я сейчас написал, будьте здоровы, и в группу соответствующую записи курсов, и просто отвечающему за это человеку.
Ага.
Но он пока не прочитал, я не знаю, может, спит еще, конечно.
Да. Ну тогда это серьезно. Не, ну на самом деле, как бы лекцию просто вам прочту, а если что, видео-то там есть с прошлого года.
Ну, на худой конец доска тоже сохранится.
Ну и на худой конец в воде можно держать. Вот поэтому особо я в этом месте велосипед не придумал. Ну что, давайте начнем.
Ну, давайте.
Вот. Ну тогда я на русском буду. Вот, но как бы мы сейчас будем заниматься кольцами. И вот мы увидим на самом деле, что, ну вообще говоря, мы работаем обычно в парадигме неутровых колец, да, и практически всегда у нас кольца неутрового модуля конечно порождены. Ну, мы так, ну, конечно, мы делаем вид, что работаем в общем случае, да, ну, произвольно. Но как ну, так сказать, если у нас что-то не получается, так сказать, первым делом мы готовы наложить естественные условия, как артинность и неутровость. Вот. Ну и как бы оказывается, ну вот артинность, да, то есть, ну, напомню, что это следующее свойство, что неутровость у нас есть возрастающая цепочка идеалов, и она, любая возрастающая цепочка идеалов стабилизируется, а артиновость это любая, то есть артинал.
Может, лучше писать на английском?
Ну давайте, да, то они еще расстроятся. Если любая убывающая цепочка стабилизируется. Вот, но и оказывается, hello. Yeah, so and if you have this, usually we assume Noetherian property, and if you are when you are considering Artinian rings, one can assume Noetherian property and Artinian. And but surprisingly, yeah, and we have noticed that Noetherian property doesn't imply Artinian, so Noetherian.
Секунду, разве не наоборот вложение должно быть в цепочке?
Да, убывающее. Спасибо. So Noetherian does not imply Artinian. We have very easy examples referring to polynomial rings. Yes, so for example, so almost where you can consider principal ideal, which is not important, usually you have the property that the sequence of ideals is infinite and does not stabilize. Yes, so this does not stabilize. And surprisingly, that if you have Artinian rings, so they could be, one could think that they are very complicated, but Artinian implies Noetherian. So, theorem that we will be discussing today. So, Artinian ring is also Noetherian. And we shall be doing it step by step, actually by analyzing the structure of Artinian rings. So we shall be discussing their structures. We shall have their, well, almost classification, and we shall see that this will imply a theory, and of course, in a sense, it is conceptual proof, but you have to more or less describe what are Artinian rings. It is not just for free. Yeah. So let me start by noticing the following. So proposition. So there is a, so every prime, so suppose A is Artinian. Then any prime ideal is maximum. Prime ideal is maximum. So here also it is important to notice that here any non-trivial prime ideal. So for example, one can think about, so this is not example of the property of Artinian rings. For example, in the polynomial rings, you have also prime ideals, yeah. So prime, and also there is zero, yeah. So zero ideals, and you can notice that here prime ideals are maximal, but you have also zero ideal which is maximal, since you do not have zero divisors. Ой, извините, я тут поле хотел поставить. Вот, so you have zero ideal, which is, so you do not have zero divisors, so zero ideals is also prime, but not maximal. So, so you see that this property is more special. So Artinian rings, for example, if you have if you have domain in the Artinian rings, then zero is zero is prime ideal, and it should be maximal. So there is no option. So let me discuss the proof. So suppose you have prime ideal P. Prime ideal. Then you may pass to E mod P, and notice that it is the main. And also notice that if you have a surjective map of the rings, then the image of the ring is also have the same property. So if the first ring is Noetherian and the second ring is Noetherian, if just if you have A modular I, so surjective homomorphism. Yes, so right, A modular kernel of phi. That's so subjective. Yeah, so, well. Well, this is just, this is just standard projection, and then a surjective homomorphism is of this form. Then if A is a Artinian, then A modulo I is Artinian. Since given a sequence, decreasing or increasing, you can pass to pre-images. Yeah? So you see that in order to prove that any prime ideal is maximal, we have to establish that this A mod P is a field, so that any element is invertible. Yes, so we have to see that A mod P is a field. So any element is invertible. And this, of course, can be so given an element that you want to invert. Yeah? So you can just consider the sequence of, already we have seen a natural sequence starting with x, decreasing sequence. So this sequence of powers of the ideals generated by powers of the element. So x is so this A mod P is Artinian. Then it stabilizes. Then at some step you will have xk is equal to xk plus 1. But for us, what does it mean? So this ideal is smaller. In general, this ideal is larger. So xk can not belong to the. It may happen that xk do not belong to this small ideal, but if it belongs, then it is written as y times xk plus 1. Yeah, so then there exists y, some element with this property, and this of course implies that xk times 1 minus yx is equal to 0, and since you do not have 0 divisors, so since we do not have 0 divisors, in A mod P, this implies that x is not 0. So y1 minus yx is equal to 0, and then y is inverse for x. Yeah? So this really tells you that that if you have domain, then any element should be invertible, and then of course in the Artinian rings it may happen that you do have also nilpotent elements. But this tells you that when you factorize by maximal ideal, it will of course contain all, and actually any prime ideal, it contains nilpotent elements. And this equality that is true in general, it gives you that so that this is invertible. So this so either after reduction, so if you write down this equality in Artinian rings, what you will have after reduction, it will be either identical to 0 because x will be 0 there, or you will have the quality that will give you inverse for your element. So then the next step is to say that just now where all ideals are, all prime ideals are maximal, so the proposition is if A is opinion, then the number of maximal ideals is finite. Ну как здорово, что у нас все пришли, а то у нас трансляция. Yeah, so if so the proof, yeah, so of course if it is clear that if you have infinite number of maximal ideals, so infinite number, yeah, so the idea is to construct the sequence, decreasing sequence, and it is clear what it should be. You just can intersect all of them one by one. Yeah, so it may happen that intersection of maximal ideals, yeah, of course it can contain 0, but it may happen that this is not empty, yeah, but so for example, so if the ring is has nilpotence, yeah, so then you will have still in this intersection you will have elements. So this is decreasing sequence. So since A is opinion, this implies that that sequence stabilizes. And at one point you will have that, so this means that you will have the following property. Yeah, but this of course implies, so this implies that mk plus 1 is just the subset of the intersection. Yeah, and we have the following property that if you have, yeah, so suppose you have, yeah, so notice that ой, извините, я неправильно. So this of course that adding mk plus 1 doesn't throw away any element, so it should contain all elements of m1 and k. And we have the following lemma that we have proved but yes, so I shall recall it without the proof. Yes, so if you have P is a prime ideal that P contains the intersection of ideals, then it implies that P contains some I.
Кажется, что трансляция на самом деле идет, просто она скрыта почему-то на сайте.
То есть это вам написали, да?
Да.
А доска правильная?
Я сейчас спрошу.
Да, если можно. Ну, как бы. Доска первая. Неправильно?
Ну,
Ну что, да, то есть, понятно. О, отлично. Или как? Или там
Там еще в уголке камеры можно быть.
в уголке камеры, ну это не серьезно, если что, в камеру. Ну, в смысле, это вот буквально трансляция наша.
да, кажется, она буквально так выглядит.
Понятно. Ну, отлично. Хорошо. Вот, so if you have this prime ideal that contains, so if you have, so P should contain I, yes, so notice that it is proved as follows, so you have, if P doesn't contain, there will be, in each EK, there will be an element which is outside of P, and their product will be also outside of P. Yes, so that will give you this lemma. And this implies that, so by this lemma, this implies that mk plus 1 contains some mi for some I. And since mi is maximal, this implies that they are equal, and, which is contradiction. So there is only a finite number of such ideals. Yeah. So next thing is will be the following. So idea is to how we should study our rings. Yes, so notice. Yes, so maybe I shall start with the lemma. Yes, so so remark. So if you have A is Noetherian, yeah, so you can consider nil radical, and then nil radical is nilpotent ideal. Yeah, so in so that means that the power of this ideal is equal to 0 for some n. And this is actually what? This is this follows from being finitely generated. So follows from this holds even in under less strict assumptions. So so weak assumption. That nil radical is finitely generated. By A1, AM, and if that this ideal is equal to 0 will mean that the product of A1 tilde etc. A and tilde is equal to 0. So nilpotence follow from the fact that you can write down A1. So each element here in the product can be written as B11 A1 plus B 1 M AM, etc. B N 1 A1, etc. plus B N M A M. And this is just a polynomial. So this is a sum of polynomial in Bij, which is not interesting for us. And here you have the product of elements, alpha 1, etc., am, alpha m. And if degree so if ni is just the elements for which the elements are nilpotent, yes, so then if the sum of these numbers is bigger than the sum of nilpotence degrees, yes, so just I shall do the better, so the rough estimate. Yes, so of course you can subtract m and add 1 to this number. So this implies that all monomials are 0, and this implies that a1 tilde, etc., an tilde is equal to 0. Yes, so but this observation, I would say that so it is important that this works only if the ideal is finitely generated. And a priori, if you work with Artinian rings and do not know Noetherian property, you do not have finitely generated. So that's why if we think that our ring will be Noetherian, then it is so it is logical. So one can expect that never-radical is nilpotent, and this is precisely the following proposition. So if A is Artinian, then never-radical of A is nilpotent. Nilpotent in a sense that it is nilpotent ideal, of course. Yes, so let us prove it. Yes, so yeah, of course. First of all, you start with the sequence of ideals. You just raise them to the power. Yeah, so this yeah, so the problem is that yeah, so if this yeah, so this sequence of course stabilizes. So sequence stabilizes. But if it stabilizes when the last element is 0, we are done, but a priori it can stabilize at some step. So nil radical of AK is equal to nil radical of AK plus 1 in the power. And we can put that this is equal to J. So we have to prove that actually J is 0. So let us prove that J is 0. So this and again I would say that notice that actually I have forgotten, did we formulate Nakayama lemma or we haven't? No. Okay, so then I will omit this for a moment. Actually there is some lemma that will tell you, this is called Nakayama lemma, that will tell you that as soon as you have this kind of equality, so this, and even it is a little, it is more a general statement, it will imply that this element is 0. But this is under assumption that the ideal, that the module you are considering is finitely generated. And a priori we do not assume Noetherian property, and this does not help us. So let me write it as the warning, and I shall return to this place later. So warning that we cannot use Nakayama lemma since nil radical is not assumed to be a finitely generated module. So why I'm making this remark? Because when you start learning something and when you read, so you always have the question, why the proof is much more complicated than you expect, and here you have to do this remark. But that's okay. So what you have, so with J, but notice that this ideal satisfies some kind of idempotent property that J square is equal to J, because this is... Да.
Формулировать мы лемму Накаямы так и не будем пока. Формулировать
Потом просто там, я не хочу открываться, давайте я вот это закончу. Давайте мы как бы Артиново кольца закончим, и вот когда мы будем обсуждать обратное следствие, можно просто наложить некоторые условия, сказать, что Артиново нульмерное кольцо, Нётерово нульмерное кольцо будет Артиново, вот как бы, чтобы это вывести, там можно использовать тоже, в смысле, что мы пока будем там это обсуждать, и поговорим заодно о Леме Накаяму. So notice that this is nil radical of K, and this is nil radical of A in the power 2K, and notice that you will have the sequence. So already you have stabilization, so you have the equality of these two ideals. So notice that this property can be specified as follows. So just consider the set just of B, so ideals, so such that G times D is not equal to 0. Yeah. So this, so of course, so this set a priori could be empty. Yeah. So, but
So what is this set?
что?
What is this set?
The set of ideals. So B is ideals, so consider just consider the set of ideals B inside A such that this property. Yeah, so notice that a priori this set could be empty, but G square, for example, if you have only maximal ideal and it is already nilpotent, yeah? But notice that it is not empty. Since for G you have this property, yeah? So this is G and not equal to 0. Yeah? So that was the motivation. And notice that if you have Artinian property that so this set Artinian property so for the any chain stabilizes, yeah, any decreasing chain stabilizes of ideals, yeah. Plus term lemma implies that any set has a minimal element. Any set has a minimal element. Now, so if you have because it falls, so any chain of ideals, any decreasing chain has minimal element. So just meaning that if more or less if you do not want to be very strict, you can say that if you have the ideal with this property, then if it is not minimal, you can take small ideal, etc., and you will construct the chain. If this process do not terminate and you cannot take the smallest ideal as possible, then this chain will be infinite, but it has to stabilize. So at some step you will have the ideal that is minimal, yeah, because otherwise you take it and take the smaller one. So this process will just be so you can just proceed with this process. So this implies that, yeah, and in particular it is clear that if so this property is just So it is sufficient to know for one element in the ideal. So it is clear that if B is minimal, then B is equal to X. Some ideal that since of course G times B not equal to 0 implies the existence such that G of X is not equal to 0, yeah? But what is non-trivial, why we have to, so a priori it is clear that this should be, that if you have, so that minimal ideals are of this form, but it's not, a priori we have to say something this, about this general property, I mean this general notation, was used because a priori it is not clear that without Arcanian property, it is not clear that this principal ideal gives you minimal ideal. Yes, so because it may happen that the ideal is so this property will hold for some x times y, and just you a priori it may happen that this process go to infinity and you do not stabilize. I mean, if you do not assume something. So now, now notice that so gx, so that means that gx
Почему все-таки
Да.
идея порождения элементом x будет минимальным?
Не, ну просто из-за того, что у вас вот это не равно нулю, просто у вас есть какой-то элемент, который... Да.
Если он порожден не одним, то да.
Да, ну значит, вы можете его взять в качестве идеала уже, да?
Всё.
Но и все, как бы, и это будет тот идеал с нужным свойством, который, вообще говоря, будет меньше, чем b. Но как бы почему вот я что-то говорил вообще о неглавных идеалах априори? Ну, потому что мне нужно было условия стабилизации, да? Но как бы, то есть мне нужно было проговорить условия стабилизации, которое говорит, что у вас все равно есть минимальный элемент, потому что, вообще говоря, даже наличие такого элемента не говорит о том, что, ну, вот, идеал, как бы, может так оказаться, что вообще все степени x не аннулируют g. А это значит, что вы просто можете идти дальше и дальше, и все. Ну, как бы.
Ну, да.
Вот, да, ну, более того, как бы, so we can also assume that, so in this property, we can also assume, that B is a subset of G, yeah, because this, yeah, so in the beginning, yeah, so because we have at least element G square is not equal to 0, so in previous step, yeah, we can. Ну это, да, ну тут, кстати, это даже не надо, да, извините. Но просто как бы дополнительно можно как бы это читать, но это не нужно. Yeah, so gx is not equal to 0, but since g square is equal to g, yeah, so this implies that g square x is not equal to 0, yeah, because it is j times jx, and yeah, sorry. So that this implies that this is not equal to 0, yeah, so this is tautology. But notice that jx, j square x, is equal to jx times x. Извините, times g. And notice that this is non-zero, so it contains non-zero elements. And this ideal is smaller than x. Yeah, so it is a subset of ideal generated by x. So since x is minimal with property bg is not equal to 0, and you see that gx gx satisfy b tilde g b tilde is not equal to 0. Yeah, so this implies a priori that gx is smaller. So this implies, and since gx is a subset of x, ну то есть вот извините, тут просто это идеал порожденный. So this is just ideal generated by g elements of g times x. So since it is a subset of x, this implies that gx actually is equal to x. This implies that gx is equal to x. And element-wise, this means that so this implies that x belongs to gx, and this implies that x is written as y times x. Yeah, because the whole where y is the element of J. And this process can be notice that y is nilpotent, so this process can be just repeated. So this implies that x is equal to y times x is equal to y times x. I change x for yx, etc. So you can repeat this procedure, etc. So to get that this is yk times x, and notice that since y is in J, so since y belongs to J, we do not have to forget that y is nilpotent. So y belongs to nil radical. So this was the power of nil radical. Вот тут я зря k использовал, ну дайте я там использую, потому что у нас было. And this of course implies that so this implies that there exists m, that ym is equal to 0, so this implies that x is equal to ymx is equal to 0, which is contradiction. So this implies that j is equal to, so this implies that j is equal to j squared is equal to 0. Okay? And which gives you, so this implies that nil radical of a to the power k is equal to 0. So this, yeah, so notice that this, if you think about non-commutative algebra, so this also works in non-commutative algebra. This argument more or less works in non-commutative algebra, and also you may notice that yeah, so we have the following observation, that if you have an important element, then it is invertible. So also we can argue like this, so that already if you have x times y times x is so sorry. So I want if you have nilpotent element, then 1 plus this nilpotent element is invertible. So just one can say that if you have x is equal to yx, this implies that 1 minus yx is equal to 0. So since y is nilpotent, then 1 minus y is invertible. This implies that x is equal to 0. So this is just a remark, but one can just so one shouldn't derive this specifically. So yeah, so this this is about nil radical. So what is the benefit? Why we really cared about this thing? So now we can pass to structural theory of Artinian rings. So structural of Artinian rings. Yeah, so notice that we have Chinese remainder theorem. That was stated in the following form. So if you have ideals that were pairwise to prime, then we have so ai plus j is equal to the whole ring. Yes, so we have the following morphism to the sum a modular ij, and this is surjective map, so this is fine. And the kernel of phi, so it is of course the intersection of all ideals, but we have learned that this intersection is a product, also is a product. And also we have learned then if you have just plus additional property. If you have ideals J1 etc. Jk such that the sum is equal to the whole ring, so that they are coprime at the whole. Yes, so that this implies that for any kj's, so their powers are coprime. Well, mj's. So saying that so that the ideals. So in particular, if you have two ideals, so you that they are coprime, that their powers also will be coprime. Here is genius remainder theorem. So let us apply it to our case. Now, if you have A is Artinian, then what do you have? We have a finite number of maximal ideals. M1, etc. Mk. Of course, since they are maximal, so Mi plus Mj is the whole ring. So since they are maximal, and of course, this implies that you can take their powers, and they are also the powers are also pairwise coprime. So also pairwise coprime. And of course, what I want to do, so a priori, you may map. So you may map A to A proposition. So you may form the precisely the map that is written in Chinese remainder theorem, but notice, so if you consider, so I want to have some structure of A, so here this kind of sums. But of course, if you take A and you map it precisely in A modulo Mi, so you took all maximal ideals. This map is surjective, but it can be not injective, since you can have nilpotence, and the kernel of this map is intersection of all maximal ideals, and you have nilpotence that are contained in this map. But if I take, so I claim that I can take very large powers. So for example, if so this map is isomorphism, for n is equal to nilpotence degree, so such that nil radical in the power n is equal to 0. Proof. So how we can prove it? Yeah, so what we have to do is to prove that. So we have to see that kernel of phi, which is intersection of all mi n, is equal to 0. Yeah. So let us write it. Yeah, but notice that when you are writing down like this, yeah, so there is a slight problem. So of course you want to, so notice that nil radical, so recall that nil radical of A is equal to intersection of prime ideals, so by the theorem that we have proved, but it is also intersection of maximal ideals and finite number of them, so since any prime is maximal. But so the problem here that when you write down this thing, so n is standing here, so you cannot, when you are speaking about intersection, you cannot take n out of the intersection. The raising to the powers doesn't commute with taking the intersection. So the idea is to make this required changes. So this is equal to the product. And this follows, so since mi n and mj and a pairwise coprime. So a coprime, yeah, so that all ideals standing in this intersection, so that they are coprime, so you can change intersection for the product. Yeah, so when you are speaking about the product, so now it becomes so it commutes with raising powers just because product is just putting ideals, and when you take a product of ideals, it commutes. So it is commutative product. Yeah, so you can just in commutative algebra, yes, so you're taking the product of ideals is commutative since it is commutative on the generators. So on the elements generating such the product of ideal. And this implies that this is just product of mi in the power n, and then you again use that mi pairwise coprime, to write down intersection here. And this implies that this is nil radical of a in the power n is equal to 0. So that proves us the claim. Yeah. So so now you have mapped so a in the product of in the product of the rings. So this is isomorphism. And what can be said about A modulo Mi? Yeah? So this notice that so proposition. So the ring A modulo. So if A is Artinian, this implies that M is Artinian local ring. Oh, извините, ну тут степень написано. Иначе я бы в поля, да, отразился. So, if M, A is Artinian and M is maximal ideal, yeah, so I claim that this is Artinian local ring. So local means that there exists only one maximal ideal. So this property, yes, why it is true. So yeah, so this actually gives you some kind of structural theorem that says that if you have the Artinian ring, it is direct product of Artinian local rings. Yeah, so this simplifies the situation. That's it. Yeah, so suppose M tilde is inside A modulo Mn, so is another maximal ideal. Yeah, so notice, yeah, so already this ring has a maximal ideal of the form M modulo Mn is maximal ideal. In A modulo Mn. And this implies, yeah, so if you take pi, yeah, so that just this projection, yeah, so the preimage of pi is maximal ideal in A, because this map is surjective. So let me put them double tilde. And you notice that this implies that M double tilde plus M, it is equal to the whole ring. Yeah. This is evidently so, since they are all maximal. But yeah, so actually this implies that so since M tilde is maximal, so already you can write down this with not even using the lemma, that you can raise n to the power and notice that since we assumed that mn wasn't the нет, ну тут как бы все-таки нужно это проговорить, да, что so if you have this kind of property, this implies that m tilde times mn is equal to a, also equal to a. And this is contradiction because this means that m tilde m double tilde maps surjectively to a, and so this was that if you apply pi to m tilde, if you reduce m double tilde modulo mn, so this is equal to a modulo mn, and which is contradiction because double tilde was proper maximal ideal, so it was maximal, it wasn't, it couldn't coincide with a. So yeah, and this proves the lemma. So maybe let us do 10 minutes break, and after the break we shall discuss what further can be said about maximal Artinian localities. So we won't say much, but we shall see some additional properties that will help us to prove that Noetherian property, to prove Noetherian property actually. Okay. Да.
I have few doubts, so can I tell you after the class?
А? Вот.
I have few questions
Хорошо.
after the class.
Yeah, yeah.
Thank you, sir.
Мы начинаем уже?
Да. Yeah, so now we just want to start with the full situation. So you see that arctan ring is a product of regular of Artinian local rings. Artinian local rings with maximal ideals. Mi modular Mn. And so you see the following. So you just starting with this Artinian local ring, you may notice the following properties. So claim is position that this ring is Noetherian. And yes, so this just will follow from the following few observations. So recall that if you have a sequence of modules, so if M2 is Artinian, this implies that M1 and M3 is Artinian. And the same for Noetherian rings. Yes, if you know that M1 and M2 is Noetherian, so you know that M1 and M2 are also Noetherian. And also, if you have M1 and M3 is Noetherian, so that's the second. If M1, you know that M1 and M3 are Artinian, or respectively Noetherian. This implies that M2 is Artinian. So respectively Noetherian. So you can check that something is Artinian and Noetherian via checking this for submodule and its quotient. And notice that here you have the following situation. So we can consider the following sequence. So this is called filtration. So suppose you have, yes, so put. So you take the local ring, so Artinian local ring. And here you have the natural sequence, natural filtration by the powers of maximal ideals. And at some point, so since it is Artinian, so and local ring, so the last one will be 0. Yeah, because it is local. I mean, even so, at that point we have started with some kind of construction. We took the ring and factorized it by maximal ideal. But we can put out argue as follows. So here, if you have Artinian local ring, then radical of E is equal to intersection of prime ideals, which are also maximal, because M is Artinian. And there is only one maximal ideal, so the null radical consists of M, and since we have proved that null radical is nilpotent, so we have seen that the last element in this sequence is 0. But then you may notice that in the sequence, or what can be said about the sequence, so just M module mi modular m I plus 1. Yes, so it has a structure of a module, but it has a structure of a mod m module. Just because this, so since you can do the following, so for m that belongs to mi modular mi plus 1, this one, and for a in a. You can take a times m, and this is this is the module structure, but if so notice that this module structure, if you write down n plus n, where n belongs to maximal ideal, yes, so this means that this will be a times m plus n times m. So the difference will belong to m I plus 1, yeah, because m can be thought as a representative. So m is a representative of m tilde in the ith power of maximal ideal. Yes, so that you can see that this thing has natural m module structure just because m times, so because you have actually m times mi is just mi plus 1. But yes, so you have to see that you have this kind of inclusion to have this a module m module structure. And but a module m is a vectors actually. So a modular m is a field. So mi modular mi plus 1 is a vector space. And now notice that for vector spaces, yes, so that proposition that for vector space over K, the following is equivalent. Equivalent so first of all, yes, so for vector spaces also you can consider Artinian property and Noetherian property. But notice that this is all of the properties are equivalent to having, so to being finite dimensional. So that V is finite dimensional. So V is Artinian. V is Noetherian. Yeah, so it is clear that so 1 implies 2 and 3 is clear, yeah, because if you have sequence, if in the sequence Vi is not equal to Vj, then dimension of Vi is strictly larger than dimension of Vj. So so starting at dimension bounded by dimension of V, yes, so you bound the dimension of decreasing sequence, and vice versa, the same for increasing sequence. It is also bounded by so w1, w2, etc. wj. Yeah, so if wi is not equal to wj, so dimension, and you have inclusion here, so here then a dimension of wi is strictly smaller than wj. And also if you have not finitely in order to prove Artinian and Noetherian property implies having finite dimension. So if you have an infinitely dimensional space, you have to invent decreasing or increasing sequence, infinite decreasing or increasing sequence. And we can see that if you have one en, etc. basis, infinite basis, so you can put E1, E2, etc. Infinite increasing sequence.
Сейчас во второй убывающей цепочке написали то, что из minus 2 и то меньше double.
Ну да, спасибо. Вот. Соответственно, если мы хотим, so if you want to study Artinian property, you can start with the whole space and decrease it, for example, as follows. So cut out the first vector, so start the sequence from E2, etc., then E3. And etc. So you can do the shift, so you will get the infinite sequence of decreasing vector spaces. So this explains that for vector spaces, and which is rather surprising, yes, so that Artinian and Noetherian properties are equivalent, and this will now let us notice that so far we have, if we have this Artinian local ring. So this implies that, and actually we can do more general statements. Suppose A is a ring where you have the property that the power of maximal ideal is equal to 0, then you have the following filtration. And in this case, so I claim that if A is Artinian, if you have a ring with this property that if A is Artinian, so it is if and only if that A is Noetherian. So this is a special this is a special situation, but so what is more important, Artinian property implies automatically this condition, Noetherian property usually this is not the case, but one can actually give the how we can characterize this. This will be a little bit later. So if you have this sequence starting, so ending at 0, so you see the following, so that you can say that yeah, so actually you can so suppose you have Artinian ring, then all, so this, so start for example with Artinian, is Artinian. So this implies that all submodules are Artinians, Artinian modules. So this implies that mi modulo mi plus 1 are Artinian. And this, then we use that they are Artinian, and they are vector spaces over A mod A. So this implies that mi modulo mi plus 1 are finite dimensional vector spaces. This implies that they are Noetherian. And then you can start extending them. Yes, so you they are all Noetherian, but notice that so this implies that we can extend them in this way. So if you want to say something like K and L, so this can be written as follows. So you can write down here just yeah, I just yeah, so let me start, for example, with the following. Suppose you have M, and you can write down A modulo, M modulo. So so for example, you start with A modulo M M square. How you can write this down? This can be written as extension, so you can factorize by the larger ideal A modulo M, and you can yeah, actually here in this setting I can be put equal to 0. Yeah, so this is so this will mean that this is just A modulo M. Yeah? So you can write down like this. This so you have this rings Artinian, and these are finite dimensional vector spaces. So you have derived that this implies that M modulo M square and AM is Noetherian. And then you derive that A mod M square is Noetherian. Yeah? Then you can go further. Yeah, so notice that A modulo M square is not anymore a vector space over A, but so you use this because of this filtration. And then if you more generally, if you want to prove that A modular Mi is Mi plus 1 is not theorem, yes, so you just can put here. Yes, this was some kind of base of induction, so this is Mi plus 1. So we know that by induction A mod Mi is not theorem. Since Mi plus Mi plus 1 is Artinian, this implies that it is not theorem, and this implies that A modular Mi plus 1 is not theorem. That actually proves the statement. Yeah? So yeah, and this process this proves actually what? This proves that all if you take I to be finite, this is not theorem. This is not theorem. Yeah, but this process terminates here, so that so since Mn is equal to 0, so this implies that E is equal to E modular Mn, and this is not theorem. And vice versa, it is clear that you can change the word not theorem for Artina and go backwards. So use the same argument literally, without saying anything more. But notice that so this proves then we have proved that this for so if A is Artinian, so a corollary of what we have said that if you say that A is Artinian, then the product, so it is equal to the product of Artinian local rings which are also Noetherian. So this of course implies that A is Noetherian. Yeah, and what we should say if we want to derive everything in the backward direction. I mean, suppose you want to find characterization of Artinian local. So first of all, notice that you want to start with a Noetherian ring. We want to understand which condition will make it Artinian. But first of all, notice that suppose the first thing that we have derived is the following: that for Artinian ring, all prime ideals are maximal, and actually for Noetherian rings it is clear that we can have maximal prime ideals which are not maximal. So this suggests that this should be put as the condition. So suppose that So dimension of A is equal to 1, and this A is 0, and this is literally that. So we shall discuss what is dimension, but a little bit later, so that every prime ideal is maximal.
Простите.
Да.
Можете прикрыть окно, пожалуйста?
Да, что-то позадуло. Или дверь лучше. Или кто-то.
Наверное, даже это не так.
Ну давайте. Так, пока нормально? Ну,
Наверное.
ну скажите, если.
Спасибо.
Вот, So if you have this property, then I claim that A is then A is Artin. Yeah. So what is the most complicated part is to how we can derive the following thing that, for example, first of all, in order to make this reduction, we have to express A as a product of rings with the same property. Notice that we have to establish two things. First of all, just decompose. So to prove. So let me write this theorem. And this should be done in two steps. First of all, reduce to the product. So construct a product. So you are writing down as the product with the same property. So where AI are local rings with the same property. And the property, notice that, of course, Noetherian wasn't enough, so the property was the following. So we have to know that Mn is equal, so for each A, so for okay. We have to have that Mi is equal to 0. Yeah, so this if this rings behaves this property, then they are local, they satisfy this equality. So then by our previous step, this implies that since AI are Noetherian, they are Artinian. So this can be derived actually from the associate prime decomposition. So let us use associate prime decomposition. Yeah, but let me do some small remarks. Yeah, so just yeah, so actually this will be we shall use associate prime decomposition of 0, which is quite fun. Yeah, so that one thinks that so associate prime decomposition was invented to decompose give a structure of any ideal, but actually, as we have noticed, it is as complicated as to have associate prime decomposition of 0. So this, so in order to just, I want to say the following remark that notice that so if you have here you have primary ideal. So notice that it was or just yeah, so let me start with modules. So primes module. Yeah, so notice that we have the formula that, yeah, so that means that the set of associated primes of the quotient it just consists of one prime ideal. Yeah, so we can consider annihilator of M mod n. And if you take radical of it, it can be expressed as so it is just P. Yeah, so this is so notice that for general module radical of annihilator. So for finitely so M is finitely generated. So radical of annihilator can be written as intersection of prime ideals that lie in the support. This was the formula that we have proved. Yeah, so during and here you have here you have the property that minimal elements, yeah, so this is the set, and now more generally we can put this P belongs to the set of associated prime ideals because minimal elements of the support, so this can be written as intersection that P is minimal element in the support. And minimal elements of support are precisely the elements of associated ideals. Yeah, so we have the following property. You see that this means that in particular this means that M modulo n is annihilated by p to the power n. Yeah? And also if we speak about primary ideals, yeah, so you have Q inside A is primary ideal. This means that if you consider primary submodule A mod Q is annihilated by, yeah, so this is under Noetherian assumption, so P should be a Noetherian, yeah, so in case that the A is a Noetherian, so, and the module is yeah, because you have to rewrite this statement. Yes, so you have to annihilate it. So you have to see that sufficiently. So you know from here that sufficiently large power of the element annihilates the module, and but you have to in order to be annihilated by the power of ideal, you have to prove that the element is annihilated by sufficiently long product of the modules that we recalled today. So this is annihilated by p to the power n. So this implies what? So this implies that q contain. So since you have unit element here, yeah, so unit element here, yeah, so you have this implies that p to the power n is a subset of q. Yeah. So this gives you the following. So if you have if your ideal is primary, then so it should be so it is a subset of its radical. Yes, so notice that p is here. P is here is a radical of q also. So and this implies that so you know a priori that q sits between the powers of so between p and some power of its prime. Yeah. So now let us use the decomposition for 0. Yeah. So just so since A is Noetherian, then 0 has associate primary decomposition. So primary decomposition. Since notice so where radical of QIs are some PIs, so they're prime ideals, and by assumption they are maximal. Yeah, so by assumption they are maximal. So you have the following property that and this means that QI, so all QIs they sit in the corresponding maximal ideal, but they contain sufficiently large power of ideal. So this means that you can write down A, so you can map it A to the product. Yeah, so since Mi are maximal, they are pairwise coprime. This implies that their powers are pairwise coprime. And this implies that you can write down, actually here you have an I and put, so here you have each n i's that is valid for its own qi, so put n to be maximum of n i's. And this implies that it is surjective. And what is kernel? The kernel is equal to kernel of phi is equal to intersection of min. But each mi is contained in the intersection of qi. Yeah, and this so you have this kind of intersection of qi, and this is equal to 0. Yeah. So this proves that so already for this qi, this intersection is 0. Yeah. So since qi formed the composition of 0. So this implies that so this implies that phi is injective. And then you see that in each ring, so in each, as we have seen that in each mi, this is a local ring with maximal ideal with only maximal ideal mi modulo mi in the power n, and it has the property that a power is equal to 0, so its power is equal to 0. So this implies that Noetherian implies Noetherian Artinian property. So we have to see here, yes, so that actually what is associated prime decomposition? It is decomposition into irreducible components of the variety. And morally, dimension 0 means that the variety consists of points, a collection of points, and you just decompose it into the union of points and Noetherian. So union of points has evident. So if evident Artinian property, so that we have discussed here. So this proves the statement. So we have, just let me look. I have said what I wanted. Yeah, also, just I want to say another additional property which is important for understanding proposition is also how you can characterize Noetherian rings, Artinian rings. Suppose A is Noetherian. I want to characterize Artinian rings. Yeah, so Noetherian rings with maximal ideal. So I do not assume that it is local. But a posteriori it will be local. And so suppose you have a Noetherian ring with a maximal ideal which is nilpotent. Which is nilpotent, which consists of nilpotent elements. Yes, so which such that M sits in a nil radical of A. So this implies that A is Artinian. Yeah, so on previous step we have said something about yeah, so on previous step we actually was discussing this. So how to first of all decompose E in the product of such rings. But if you a priori know, so I mean the general for general ring, just it yeah, so for yeah, so let me prove it. Yeah, so consider nil radical. This is a intersection of prime ideals. And here, of course, so by assumption, you have the property that M sits, so M sits in this intersection of ideals, but M is one of the factors. So, but notice that M is one of the factors. Yeah, so you see that this implies that nil radical, so that there is only one factor corresponding to M. Yeah? So this implies that so in this formula all spectrum A consists only of M, and this yeah, so this implies that ring is local. So you know that this is Noetherian. And the power, so this implies that nil radical is equal to 0. Yeah, so which is for some n. And this, by previous assumption, this implies that A is RP. So by previous theorem.
Как еще раз мы поняли, что больше простых идеалов нет?
Не, ну просто у вас есть, вот смотрите, у вас есть пересечение, да, по всем простым, которые, вот тут, которые,
Ой, да,
и оно именно содержит m, да, но m лежит среди этих, поэтому если тут есть другие идеалы, в них есть элементы вне, либо они меньше, ну, все меньше m, тогда это включение, ну, тогда это пересечение все равно меньше, чем m. А если они имеют элементы вне m, то тогда, ну, нет вот этого включения. Вот, поэтому, как бы, просто у нас получается, что вот из этой формулы у нас нил-радикал, во-первых, совпадает в точности с m, и мы видим, что это локальное кольцо, а для локальных колец мы знаем, что локальное кольцо со свойством степень идеала равно нулю, мы знаем, что оно как раз арти. Вот. То есть, как бы, вот это вот свойство, да, что радикал, ну, в смысле, что максимальный идеал нипотентен, это такое очень сильно ограничительное свойство. То есть, ну вот, этим мы, кстати, вот это выделяю как специальную лемму, потому что я хочу воспользоваться этим. Yeah, so now I want to discuss Krull theorem, Krull principal ideal theorem. And actually what we were talking about was some kind of preparation for this theorem. Yeah, so what does it says? It discusses the properties of, so for the rings we are introducing dimension. So dimension of A is the following, so it is a sequence so you can is the maximal length of the sequence of prime ideals. Yeah, so notice that for example, if you are speaking about polynomial ring, so two-dimensional space, yeah, so it will correspond to affine space, just affine space, where the dimension is just what? So you have the following sequence, so that the dimension is 2, so you start with 0 ideal, yeah, so it is P0. So it corresponds to, so the quotient by 0 ideals is correspond to the whole affine space. So then you have prime ideal, which is x, for example, x equal to 0.
Как будто будет.
Да, да. And then you have the maximal ideal generate. Oh. Yeah, so this is P1 and this is P2, yeah? So, this corresponds to the flag of the subspace consists of points and the line x equal to 0, yeah? So, the point x equal to 0, y equal to 0, and more generally you can take, if you have polynomial ring, you can take this sequence of flags and this sequence of line subspaces, so that will give you the sequence of ideals. But notice that, yeah, and if this, yeah, so of course a priori this sequence can be infinite. So we say that it is of infinite dimension. And also, one should say that it's so there could be a quite different flags that so you start with different points, and moreover the variety that those coordinate rings you are considering, it could have different components. And different components have different dimensions. So sometimes one put to that the last one. Make some kind of so that they make the dimension dependent on the last element in the sequence, on the point. So you for varieties, this corresponds to so let me write down this geometric interpretation. This is constructing flag of varieties. Here you start with the this. You start with closed irreducible varieties. Yeah, and you look at the maximal sequence, but notice that, so of course the first one is a point, and you may think of dimension of x and the point. Yeah, but by fixing the first element in the chip. Yeah, so just flag is flag, so a maximal length of flag starting with x, z. So you have you have this kind of sequence, And so here, of course, for the ring, you can do the same thing. Yes, so you can consider dimension starting with so if ending at this maximal ideal, and you can consider the chains that stops at M. Yeah. So this yeah. So that is about this kind of definition. And if you want to consider the quotient A modulo I, yeah, so then that means that in terms of A, you have to consider the intermediate chains between I and the ring A, yeah, if you want to study this the dimension of this ring, since prime ideals of A are actually prime ideals of A mod I containing I in the correspondence with prime ideals that contain I in A. So this now we have the following question that just if you start with A, what is dimension of A mod A for principal ideal? So that means geometrically, so if you have variety x, you have function f equal to 0, and you want to understand what is dimension of the zero set. Yeah? So, and the crude dimension theorem says morally that this dimension should be decreased by 1. So if this equation is non-trivial, so this dimension is decreased by 1, but not more than by 1. Yes, so that that means that one says that co-dimension of ZF is equal to 1, just for example, if X is irreducible, and so for us, this one can reformulate this theorem in algebraic terms, and this is called principal ideal theorem. It says the following. Suppose P is so A, so it's some element. Suppose that P is so we shall assume that A is Noetherian. So suppose P is minimal ideal containing A, minimal prime ideal containing A, then just for any so any ideal that is contained in P is minimal. so then any prime ideal that is contained in P is minimal. So that means there are no prime ideal Q. So there are no prime ideals that are contained in Q. So this means this formulation is a little bit tricky. Let me just let me explain a geometric interpretation of it and why it is formulated in such a way. So the problem is that this thing says something about codimension of components. Yeah, so that means that first of all, what is so morally? Suppose you have spectrum of A.
Сейчас P минимальный в каком смысле?
Но P минимальный, значит, между А и P нету других простых идеалов. Ну, то есть как бы именно среди простых, да.
Именно между А и P, да?
Да. Ну, да, то есть давайте напишем, что there are no ideals, no prime ideals, between A and P. Yeah, so notice that why this condition is important. Yeah, simply because so from the viewpoint of geometry, the equation f squared equal to 0 gives the same zero set as f equal to 0. But and then what about P? Yeah, so this P. So you have condition that P contains F. Then this means that P is component from the viewpoint of associated prime decomposition. That this means that P is component of the zero set. Yeah, but of course, yeah, so you may start with f squared, yeah, and you see that the P will be the same because P is a radical ideal. Yeah. But notice that in between f and so in between P there will be ideal f is equal to 0. So this shows that explains why this minimal is taken not among all ideals, yeah, but among among prime ideals. Yes, of course, there could be ideals in between A and P, but they are not they're not prime. And of course, yes, so there could be some. So P should be non-trivially generated. Yes, so for example, you can take another generator, and instead of generating the whole ideal, you could have power of this generator, which which gives you larger ideal than generated by A, but smaller ideal than by B. So, and notice, so what does it mean? So that you have zero set, and you have this P, and what does this mean Q for us? Q is, so you take the zero set A equal to 0, you have P, this is minimal prime ideal, and Q correspond the component containing this zero set of the function. So the thing is that the spectrum can have several components, and the function can have zeros also on these components. But of course, if component is of smaller dimension, yeah, so this means the following. So the zero set of the function, you cannot speak about, I mean, you can speak of dimension, but it is, so at least you cannot say something uniform about its dimension, because you have, in A, there are several components, yes, so and the function behaves, so if these components are disjoint, the function behaves differently in each component. And of course, so to say that P is so that each component of the zero set is of codimension 1, so this so the dimension is decreased by 1. That means that it should be done in comparison with each component, and in order to specify this component, so you are choosing Q. So that's why it is formulated in a little bit strange way. Yeah? So yeah, actually we're out of time and the proof is lengthy, so let me just stop here with this theorem. And also let me, so since on not on the previous class, but on the class before previous, yeah, so there was a mistake in the lecture, so let me correct it and precisely correct it in the paper. In the corresponding sheet, so let me do it. Сейчас я еще поправлю и, ну, просто пару слов скажу, да. So, so this was, то есть это какая была лекция? 14, не на прошлой, да, 15. Тут есть имя? Сейчас. Может, недавно. Вот, 15. Да, но вот, so there was a mistake here, yeah, so this when we started Jacobson rings, so and started proving the theorem, yeah, so yeah, here, yeah, so this Yeah, so here, yeah, so we noticed, so we discussed the Jacobson property of the ring of polynomials over the field. Yeah, and then the claim is that we have to derive the following. So we have to take 0, and so which is prime ideal, and we have to write it down as the intersection of maximal ideals. And notice that in this case, the maximal ideals are described as the irreducible polynomials. And notice that if you have so f1, fk, so intersection of irreducible polynomials, so ideals generated by irreducible polynomial, it is just the product. Yeah? So notice the ideal corresponding to the product. So I claim that if you have, first of all, I claim that there are infinite, so there exists infinite irreducible coprime irreducible polynomials in this Euclidean ring, and the reason is the following, that if there are finite, then so infinite coprime irreducible polynomials. So if you have finite number of them, so finite number, then if you take their product and add 1, this will have prime factor, have a prime factor, g, which is coprime to of the polynomials, because yeah, so I mean that I have taken the product, added 1, so the reducible factor will be coprime to all of these polynomials. Otherwise, it will divide the product, and you will have 1 as just the result of the division by g. And this now we have to see that if you take the intersection of all, so if you have infinite sequence of f1, etc., fk, infinite sequence of factors, 0 will be equal to this the intersection. And the reason is the following. So if f, since your ring is Euclidean, it is factorial, so there will be unique way to represent f in the product. So any f is represented uniquely in the product, and so any f can be divisible only by finite number of factors, only by finite number of factors, so it does not belong to the ideal generated by the product for L sufficiently large. Yeah, So it is, if you pass to algebraically closed case, this will mean simply that f will cannot have an infinite number of roots. Yeah. So sorry for this mistake. It was corrected in the chat, but not corrected on the lecture. Finish. На следующий раз будет теорема круга.